Picture this: a civilization so advanced that it harnesses the power of an entire galaxy. Every star, every planet, every cosmic energy source, all under their control. It sounds like something straight out of your favorite science fiction epic, doesn't it? But what if I told you that scientists have already developed a scientific scale to measure our progress toward this incredible achievement? In the vastness of space, amid billions of galaxies and countless stars, humanity has always dreamed of reaching beyond our earthly boundaries. Today, we're diving into one of the most captivating and visionary concepts in modern astronomy: the Kardashev Scale. This isn't just another scientific classification system. It's a window into our potential future among the stars. Think about this for a moment. Right now, as you're watching this video, you're witnessing the evolution of a potential interstellar civilization in real time. Yes, I'm talking about our own civilization, humanity itself. Every technological breakthrough, every scientific discovery, every step forward in our understanding of the cosmos brings us closer to ascending this cosmic ladder. The Kardashev Scale isn't merely an abstract concept gathering dust in some scientific journal. It's a cosmic roadmap charting humanity's potential journey from a planetary species to masters of the stars. It serves as both a measure of our current capabilities and a testament to our boundless potential. This scale doesn't just tell us where we are, it shows us where we might go, painting a picture of humanity's possible future among the stars. When we look up at the night sky, we see more than just distant points of light. We see our destiny, our potential, and the countless possibilities that await us as we climb this cosmic ladder of advancement. The Kardashev Scale reminds us that we're not just observers of the cosmic dance. We're participants in it, with the potential to become one of its leading performers. This journey we're about to explore isn't just about technological advancement or energy consumption. It's about understanding our place in the universe and imagining what we might become. It's about dreaming big while keeping our feet firmly planted in scientific reality. So let's embark on this fascinating journey together as we explore what might be the ultimate measure of civilization's progress in the cosmos. Let's dive into the fascinating origins and essence of the Kardashev Scale. In 1964, during the height of the space race and human cosmic ambition, Soviet astronomer Nikolai Kardashev proposed a revolutionary way to think about civilizations across the universe. Working at a time when humanity was just beginning to reach for the stars, Kardashev asked a profound question: how do we measure the advancement of a civilization on a cosmic scale? The brilliance of Kardashev's approach lies in its elegant simplicity. Instead of measuring technological advancement through specific inventions or capabilities, he focused on one fundamental aspect: energy consumption. His reasoning was clear. Any advanced civilization would need increasingly massive amounts of energy to sustain itself and expand its reach into the cosmos. When Kardashev first published his work in the journal Soviet Astronomy, he outlined 3 distinct types of civilizations. Each type represented a quantum leap in energy utilization and technological capability. This classification wasn't just about categorizing hypothetical alien civilizations. It provided a roadmap for humanity's own potential development. What makes the Kardashev Scale particularly compelling is its scientific foundation. Kardashev based his calculations on real physics and mathematical principles. He considered the actual energy output of planets, stars, and galaxies, creating a scale that's both imaginative and grounded in scientific reality. The scale's influence has extended far beyond its original conception. Modern scientists and theorists have expanded upon Kardashev's original framework, adding subtypes and even extending the scale to include Type 4 and Type 5 civilizations. These additions reflect our growing understanding of the universe and its energy potential. It's worth noting that the scale doesn't just measure raw energy consumption. It implies mastery over different spheres of influence: planetary, stellar, and galactic. Each level represents not just an increase in energy usage, but a fundamental transformation in how a civilization exists and operates. Contemporary discussions of the scale often incorporate concepts that weren't even imagined in Kardashev's time. Things like quantum computing, artificial intelligence, and dark energy all add new dimensions to how we interpret and apply the scale. Yet the basic principle remains unchanged: energy utilization as a measure of advancement. The scale has also become a valuable tool in the search for extraterrestrial intelligence. Scientists use it to guide their search for signs of advanced civilizations, looking for energy signatures that might indicate Type 1, 2, or 3 civilizations somewhere in the cosmos. Perhaps most importantly, the Kardashev Scale serves as a humbling reminder of our current status. While we've made remarkable progress since 1964, we haven't yet reached even Type 1 status. This realization helps put our technological achievements in perspective while highlighting the vast potential for growth that lies ahead. When we think about the Kardashev Scale today, we're not just considering a classification system. We're contemplating humanity's potential future, our possible paths of development, and our place in the cosmic hierarchy. It remains one of the most thought-provoking frameworks for understanding both our current capabilities and our future possibilities in the vast expanse of space. The Kardashev Scale represents more than just a scientific classification system. It's a vision of what civilization could become, a roadmap to the stars, and a reminder of the incredible journey that lies ahead of us as we continue to advance and reach for ever greater heights of technological achievement. A Type 1 civilization represents humanity's next great leap forward, a civilization that has achieved complete mastery over its home planet's energy resources. This isn't just about having advanced technology, it's about reaching a level of development where we can harness and store all forms of energy our planet naturally provides. Imagine a world where we could capture every bolt of lightning, harness every ocean wave, utilize every ray of sunlight reaching Earth's surface, and tap into the planet's geothermal energy with perfect efficiency. A Type 1 civilization would control approximately 10 to the power of 16 watts of power, equivalent to all the energy our planet receives from its parent star. Where do we stand today? According to calculations using the modified Kardashev Scale, Earth's civilization currently ranks at approximately 0.73. This means we're roughly 3/4 of the way to becoming a Type 1 civilization. While this might sound impressive, the remaining gap represents an enormous technological challenge. The difference between our current energy utilization and Type 1 status isn't linear, it's exponential. To put this in perspective, let's look at what a Type 1 civilization would be capable of. They would have complete control over the planet's weather systems, could prevent natural disasters, and would be able to build massive structures that seem impossible by today's standards. They would have mastered clean, renewable energy sources and solved the challenges of energy storage and distribution. Popular culture has given us some compelling visualizations of what a Type 1 civilization might look like. In Blade Runner, we see a world where massive arcologies, self-contained city buildings, dominate the skyline, powered by fusion reactors and other advanced energy sources. The planet Coruscant from Star Wars represents an even more advanced version, an entire planet transformed into one vast, self-sustaining city, with energy needs met through various advanced technologies. The path to becoming a Type 1 civilization involves several key technological milestones. We would need to perfect nuclear fusion, develop highly efficient solar collection systems, create planet-wide energy distribution networks, and master energy storage on an unprecedented scale. We would also need to develop technologies for weather control and climate management. One fascinating aspect of approaching Type 1 status is the transformation of our relationship with our planet. Rather than simply living on Earth and exploiting its resources, a Type 1 civilization would become a true steward of its world, managing and maintaining planetary systems as carefully as we might tend a garden. The challenges in reaching Type 1 status aren't just technological, they're social and political as well. Such advancement would require unprecedented global cooperation and resource sharing. We would need to overcome national boundaries and develop truly global systems of governance and resource management. The time frame for achieving Type 1 status is a matter of scientific debate. Some researchers suggest we might reach this level within the next 100 to 200 years, while others propose it could take significantly longer. The rate of our advancement depends not just on technological progress, but on our ability to solve global challenges like climate change, resource depletion, and international cooperation. What's particularly intriguing about the Type 1 threshold is that it represents a point of no return in civilization's development. Once a civilization achieves this level of energy mastery, it becomes highly unlikely to regress or collapse due to natural disasters or resource limitations. It marks a fundamental shift from a vulnerable planetary civilization to a truly sustainable one. Currently, we can see early precursors of Type 1 technology in development: global internet networks, emerging weather modification capabilities, increasing renewable energy adoption, and early experiments with fusion power. These developments, while impressive, are just the beginning steps toward true planetary mastery. The journey to Type 1 status represents perhaps the most critical phase in human development, the transition from a planetary civilization to a truly spacefaring one. It's a future that's both thrilling and challenging, requiring us to reach beyond our current limitations while learning to better manage and protect our home world. When we talk about a Type 2 civilization, we're entering a realm that would seem almost godlike by our current standards. Imagine a civilization so advanced that they can harness the entire energy output of their star, in our case, the Sun. We're talking about an energy utilization of approximately 10 to the power of 26 watts, a mind-boggling figure that's 10 billion times more energy than a Type 1 civilization commands. The concept of stellar engineering at this scale was perhaps best crystallized by Freeman Dyson in 1960, leading to the famous concept of a Dyson sphere. This hypothetical megastructure would completely encompass a star, capturing nearly 100% of its energy output. Picture a vast shell or swarm of satellites surrounding our Sun, each component working in perfect harmony to capture and utilize every photon of energy the star produces. The engineering required for such an achievement would be staggering. A complete Dyson sphere around our Sun would require more material than exists in all our solar system's planets combined. This has led to various proposed alternatives, such as a Dyson swarm, a vast network of orbiting solar collectors that would achieve similar results while being more practically feasible. To truly grasp the power of a Type 2 civilization, consider this. With the energy of an entire star at their disposal, they could power millions of Earth-like habitats. They could terraform planets at will, create artificial worlds, and maintain vast orbital habitats throughout their solar system. The energy output of our Sun could theoretically support a population of quadrillions of humans living in space habitats, each enjoying a standard of living far beyond our current capabilities. The technological implications are equally stunning. A Type 2 civilization would have mastered antimatter production on an industrial scale, achieved perfect matter-energy conversion, and developed computing power that would allow them to simulate entire universes. They could manipulate space-time itself, potentially creating stable wormholes for rapid transit across their solar system. Climate control would be trivial at this level. They could move planets, redirect comets, and even adjust their star's output if needed. The ability to prevent or mitigate any natural disaster would be well within their capabilities. They might even be able to extend their star's lifespan through stellar engineering. Transportation within such a civilization would likely involve technologies we can barely conceive of today. They might use solar sails powered by focused stellar energy, antimatter drives, or even more exotic propulsion systems that manipulate the fabric of space-time itself. The entire solar system would be their playground, with travel times between planets reduced to hours or days rather than months or years. The social and cultural implications of reaching Type 2 status are equally fascinating. How would a civilization organize itself when energy scarcity no longer exists? What kind of society emerges when physical needs are completely met and resources are virtually unlimited? They might develop forms of art and entertainment that utilize entire planets as their canvas, or create experiences that span the entire solar system. One particularly intriguing aspect of Type 2 civilizations is their potential immortality. With the ability to control their entire star system, they would be largely immune to natural disasters or resource depletion. They could survive their star's natural evolution by maintaining it, or even moving to another star system if necessary. The gap between our current civilization and Type 2 status is enormous. While we can imagine the steps needed to reach Type 1, the jump to Type 2 represents a transformation so complete that many of its aspects are difficult for us to even conceptualize. We're talking about a civilization that would have complete mastery over matter, energy, and possibly even space-time itself. For perspective, if we assume our current civilization is at 0.73 on the Kardashev scale, reaching Type 2 would require an advancement of our energy utilization by a factor of 10 billion. Even after achieving Type 1 status, it might take thousands of years to reach Type 2, assuming we continue to advance technologically. Yet despite seeming like science fiction, the principles behind Type 2 civilization capabilities are based on known physics. We can calculate the energy requirements, theorize about the necessary technologies, and even begin to imagine the engineering challenges involved. While we're countless generations away from achieving this level, understanding what's possible helps guide our long-term development as a species. This level of civilization represents not just an upgrade in our technological capabilities, but a fundamental transformation in what it means to be human. It's a future where we're no longer bound by planetary constraints, where we've truly become masters of our solar neighborhood, and where the dreams of science fiction have become engineering reality. A Type 3 civilization represents the pinnacle of technological achievement that we can reasonably conceptualize within our current understanding of physics. We're talking about a civilization capable of harnessing the energy of an entire galaxy, approximately 10 to the power of 36 watts of power. This is an almost incomprehensible amount of energy, representing billions upon billions of stars and their planetary systems, all under the control of a single civilization. Imagine a civilization that has mastered interstellar travel to such a degree that crossing the vast gulfs between stars is as routine as our current intercontinental flights. They would have colonized not just a few nearby star systems, but millions or even billions of them. The Milky Way alone contains an estimated 100 to 400 billion stars. A Type 3 civilization would have the capability to utilize most, if not all, of these stellar resources. The technological capabilities of such a civilization would appear nothing short of magical to our current understanding. They would likely have mastered the manipulation of space-time itself, potentially using artificial wormholes or some form of faster-than-light travel to maintain their vast galactic empire. The ability to move between stars would be essential for maintaining any sort of unified civilization on a galactic scale. Popular culture has given us some vivid, if simplified, representations of what such a civilization might look like. The galactic empire from Star Wars, with its ability to traverse vast distances quickly and construct planet-destroying weapons, offers a glimpse of Type 3 capabilities, though it's actually quite modest compared to what a real Type 3 civilization could achieve. The forerunners from the Halo series, with their ability to construct massive artificial worlds and manipulate the fabric of space itself, perhaps come closer to the true potential of a Type 3 civilization. The engineering projects of a Type 3 civilization would be staggering in scale. They might construct artificial habitats the size of solar systems, move stars to optimize their galaxy's energy efficiency, or even create artificial black holes as power sources. They could potentially engineer the structure of their entire galaxy, perhaps reshaping it to maximize energy production or create vast networks of connected stellar systems. Communication in such a civilization would require technologies far beyond our current capabilities. They would need to overcome the light-speed barrier that currently limits our ability to communicate across interstellar distances. This might involve quantum entanglement communication systems, or perhaps even more exotic technologies we haven't yet theorized. The computational power available to a Type 3 civilization would be almost unlimited. They could simulate entire universes, model the evolution of galaxies with perfect accuracy, and perhaps even understand the fundamental nature of consciousness and reality itself. Their scientific knowledge would be so vast that they could manipulate the basic forces of nature with precise control. The social and political organization of a Type 3 civilization is difficult to imagine. How would a society spanning billions of light years maintain cohesion? They might develop entirely new forms of consciousness or existence, perhaps merging biological and artificial intelligence in ways we can't currently comprehend. The very concept of individual identity might be radically different at this scale. One particularly fascinating aspect of Type 3 civilizations is their potential visibility to other galaxies. Their energy usage would be so massive that they might be detectable across intergalactic distances. In fact, astronomers today are already searching for signs of Type 3 civilizations in other galaxies by looking for unusual infrared signatures that might indicate galaxy-wide engineering projects. The gap between our current civilization and Type 3 status is almost unimaginably vast. If achieving Type 2 status might take thousands of years, reaching Type 3 would likely require millions of years of continuous technological advancement. The challenges involved aren't just technological. They include biological evolution, social development, and perhaps even modifications to human consciousness itself. The energy requirements are equally staggering. While a Type 2 civilization harnesses the power of a single star, a Type 3 civilization must coordinate the energy usage of billions of stars simultaneously. This would require levels of engineering and energy management that transcend our current understanding of physics. Even the concept of time would be different for a Type 3 civilization. With colonies spread across a galaxy 100,000 light-years in diameter, different parts of the civilization would experience time differently due to relativistic effects. They would need to develop entirely new ways of thinking about causality and temporal relationships. Despite seeming like pure science fiction, the concept of Type 3 civilizations helps us understand the ultimate potential of technological advancement. It serves as a reminder that our current capabilities, impressive as they might seem, are just the tiniest fraction of what might be possible. The gap between our civilization and Type 3 status represents not just technological advancement, but a fundamental transformation in what it means to exist as an intelligent species in the universe. In the vast cosmic ocean, humanity has long wondered, are we alone? This question has driven some of the most ambitious scientific endeavors in human history, and at the forefront of this search stands Dr. Jill Tarter, a pioneer who has dedicated her life to the search for extraterrestrial intelligence. Dr. Tarter's work has been nothing short of revolutionary. As one of the founders of modern SETI, she transformed the field from a fringe scientific pursuit into a respected scientific discipline. Her work inspired Carl Sagan's novel Contact and the character played by Jodie Foster in the subsequent film. But beyond these popular culture touchstones, her real legacy lies in developing rigorous scientific methods for detecting advanced civilizations. The search for advanced civilizations employs a fascinating array of detection methods. Radio astronomy stands as our primary tool, listening for artificial signals that stand out from the cosmic background noise. The rationale is simple yet profound. Any sufficiently advanced civilization would likely use electromagnetic waves for communication, just as we do. Scientists specifically look for narrowband signals, which nature rarely produces but technology commonly creates. Optical SETI represents another fascinating approach, searching for artificial light sources or laser signals from distant stars. An advanced civilization might use powerful lasers for interstellar communication or space travel propulsion, creating distinctive light signatures we could potentially detect. Perhaps one of the most intriguing modern search methods involves looking for Dyson structures, hypothetical megastructures that advanced civilizations might build around stars to capture their energy. Astronomers scan the skies for stars that show unusual infrared signatures, which might indicate the presence of such massive artificial constructions. Technosignatures have emerged as a promising new frontier in our search. These are any measurable properties that indicate the presence of advanced technology. This could include industrial pollution in exoplanet atmospheres, artificial light patterns, or even waste heat from massive engineering projects. The James Webb Space Telescope has opened new possibilities in this area, allowing us to study exoplanet atmospheres in unprecedented detail. Yet amid all these search efforts, we face what's known as the Fermi paradox, named after physicist Enrico Fermi. The paradox is deceptively simple. Given the vast age of the universe, the billions of potentially habitable planets, and the time available for civilizations to develop and spread, we should see evidence of advanced civilizations everywhere. Yet we don't. The cosmic silence is deafening. Various explanations have been proposed for this paradox. Perhaps advanced civilizations are extremely rare, separated by vast distances of space and time. Maybe they exist but choose to remain hidden, following some cosmic principle of non-interference. Or perhaps, more ominously, civilizations tend to destroy themselves before reaching advanced stages of development. Recent research has suggested another intriguing possibility. We might be looking for the wrong signs. Our search methods are based on our current understanding of technology and physics. But a truly advanced civilization might use technologies we can't even comprehend, making their signatures invisible to our current detection methods. The discovery of Oumuamua, our first detected interstellar visitor, highlighted how challenging it can be to interpret potential evidence of advanced civilizations. While most scientists concluded it was a natural object, its unusual characteristics led some researchers to suggest it could be artificial in origin, demonstrating how difficult it might be to recognize alien technology, even if we saw it. Current search efforts have expanded to include the concept of von Neumann probes, self-replicating spacecraft that an advanced civilization might use to explore the galaxy. These could be incredibly small, making them even harder to detect, yet potentially present throughout our solar system. Despite decades of searching, we haven't detected definitive evidence of advanced civilizations. But as Dr. Tartar often emphasizes, we've only searched an incredibly tiny portion of our cosmic neighborhood, equivalent to examining a single glass of water from Earth's oceans. The search continues, becoming more sophisticated with each technological advance we make. What's particularly exciting is that our search capabilities are advancing exponentially. New telescopes, more sensitive detection methods, and artificial intelligence are revolutionizing how we scan the cosmos for signs of intelligence. We're entering an era where we can study exoplanet atmospheres, detect smaller space objects, and process vastly more data than ever before. The search for advanced civilizations represents more than just scientific curiosity. It's a quest to understand our place in the cosmic order. Whether we find evidence of other civilizations or continue to face cosmic silence, every search teaches us something valuable about our universe and ourselves. As we continue to advance our own civilization, we're not just passive observers in this search. We're actively increasing our ability to recognize and potentially communicate with other advanced civilizations, wherever they might be. When we venture beyond Type 3 civilizations in the Kardashev Scale, we enter a realm where science begins to blur with philosophy, where physics meets metaphysics, and where our very understanding of reality is challenged. The theoretical Type 4 and Type 5 civilizations represent possibilities so far beyond our current understanding that they almost transcend comprehension. A Type 4 civilization would theoretically harness the energy of an entire universe, approximately 10 to the power of 46 watts. Try to imagine for a moment what this means. Control over not just galaxies, but galaxy clusters, superclusters, and the very fabric of space-time itself. Such a civilization would have mastery over fundamental forces we're only beginning to understand: dark energy, dark matter, and possibly even the ability to manipulate or create black holes at will. These beings would likely be able to engineer reality at its most fundamental level. They might have the capability to alter physical constants, manipulate quantum fields across cosmic distances, or even create new universes. The beings comprising such a civilization might exist in forms we can't even conceptualize, having long since transcended biological limitations. Think about the progression. Type 1 masters their planet's energy, Type 2 their star's energy, Type 3 their galaxy's energy, but Type 4 would command the energy of space-time itself. They might exist in a state where the distinction between matter, energy, and consciousness has become meaningless. Their technology would be indistinguishable from what we might consider supernatural or godlike abilities. Moving even further into the theoretical realm, we arrive at the concept of Type 5 civilizations, masters of the multiverse. This classification was proposed as an extension of Kardashev's original scale to accommodate our expanding understanding of cosmology. A Type 5 civilization would theoretically have access to and control over multiple universes, existing in a state that defies our current physics models. The implications of Type 5 existence are staggering. Such a civilization might be able to move between parallel universes, engineer new universes with customized physical laws, or exist simultaneously across multiple realities. They would transcend not just space and time, but the very concept of dimensional existence as we understand it. The philosophical implications of these classifications are profound and far-reaching. They force us to confront fundamental questions about the nature of progress, consciousness, and existence itself. What happens to consciousness when a civilization reaches such levels? Would individual identities still exist, or would they merge into some form of collective universal consciousness? These classifications also raise intriguing questions about the nature of reality itself. If Type 4 or V civilizations are possible, could our universe be the creation of such a civilization? Could what we consider natural laws be the engineered parameters of an unfathomably advanced species? These questions border on theological territory, highlighting how advanced technology might be indistinguishable from what we traditionally consider divine. The concept of technological singularity becomes particularly relevant when discussing these civilization types. At some point, the progression of technological advancement might accelerate beyond our ability to predict or comprehend its direction. The transition from Type 3 to Type 4 might represent such a singularity, where the very nature of existence and consciousness undergoes a fundamental transformation. Some theorists suggest that the gap between Type 3 and Type 4 civilizations might be infinite, representing a fundamental barrier that no civilization can cross within our universe. Others propose that the transition might require evolving beyond what we currently understand as physical existence, perhaps into some form of pure energy or information-based existence. The time scales involved in such advancement are almost beyond comprehension. If humanity survives and continues to advance, it might take millions of years to reach Type 3 status. The jump to Type 4 or V, if possible at all, might require billions or trillions of years, time scales approaching the age of the universe itself. These classifications also raise questions about the ultimate fate of intelligent life. Is the progression toward ever higher civilization types inevitable for any species that survives long enough? Is there an ultimate endpoint to technological and social evolution, or does the potential for advancement extend infinitely? Perhaps most provocatively, these classifications force us to consider our own potential future. While we struggle with planetary scale challenges, barely approaching Type 1 status, the existence of these theoretical civilization types suggests the possibility of advancement far beyond our current limitations. They serve as a reminder that what we consider to be the peak of achievement might be just the beginning of a much longer journey. The very existence of these theoretical classifications demonstrates humanity's ability to conceptualize and reach for something far beyond our current capabilities. They represent not just technological advancement, but the expansion of consciousness and understanding itself. Whether or not such civilizations are possible or already exist somewhere in the multiverse, the very act of imagining them expands our perspective on what might be possible. In contemplating these advanced civilizations, we're really exploring the outer boundaries of what we can conceive as possible. These classifications serve as a mirror, reflecting back our own limitations, aspirations, and potential for growth. They remind us that the journey of civilization might be far longer and more extraordinary than we can currently imagine. Right now, at this very moment in cosmic history, humanity stands at a fascinating crossroads. On the Kardashev Scale, we currently rank at approximately 0.73, not quite Type 1, but well on our way. To put this in perspective, we're a civilization that can harness some of our planet's resources, launch objects into space, and contemplate our place in the universe, yet we haven't mastered our planet's full energy potential. This 0.73 rating tells an intriguing story. We've come remarkably far from our humble beginnings as hunter-gatherers, yet we're still far from achieving planetary mastery. We can split atoms and send robots to Mars, but we can't control our weather or fully harness our sun's energy. We're like teenagers of the cosmic civilization scale, full of potential, but still growing into our capabilities. The path toward advancing on this scale presents both tremendous challenges and extraordinary opportunities. Renewable energy stands as one of our most promising stepping stones. Solar technology improves exponentially, with efficiency records broken regularly. Wind power becomes more sophisticated, and energy storage solutions advance rapidly. These aren't just environmental choices, they're crucial steps toward Type 1 status. Nuclear fusion represents another frontier in our advancement. While we've managed to achieve fusion reactions, we're still working on making them energy positive and commercially viable. The ITER project and private fusion initiatives represent humanity's attempt to replicate the power of stars. Success in this field would mark a significant leap forward in our energy capabilities. Space technology plays a crucial role in our advancement. Companies like SpaceX, Blue Origin, and others are making space access more affordable and routine. The James Webb Space Telescope expands our understanding of the cosmos, while proposals for space-based solar power could revolutionize our energy collection capabilities. Artificial intelligence emerges as a potential game-changer in our civilization's progress. AI could help solve complex problems in energy distribution, climate modeling, and resource management, all crucial components for advancing toward Type 1 status. However, it also presents risks that we must carefully manage. But perhaps our greatest challenges aren't technological at all. Global cooperation, resource distribution, and sustainable development represent crucial hurdles we must overcome. A Type 1 civilization requires unity and cooperation on a planetary scale, something we're still struggling to achieve. When we consider progress on a cosmic scale, we must think beyond simple technological advancement. True progress involves sustainable development, ethical considerations, and balanced growth. It's not just about consuming more energy, it's about using it wisely and ensuring our advancement benefits all of humanity. Interestingly, our current position at 0.73 represents both hope and warning. We're advanced enough to understand our potential and our limitations, yet we're also at a critical juncture. Our technologies are powerful enough to cause significant harm if misused, but not yet advanced enough to guarantee our survival against major cosmic threats. The challenges of climate change, resource depletion, and environmental degradation serve as crucial tests. Overcoming these challenges isn't just about survival. It's about proving we're ready for the responsibilities that come with greater power. Each solution we develop brings us closer to Type 1 status. Looking at our trajectory, we can identify several key milestones ahead. Achieving fusion power, developing a global energy grid, mastering weather control technologies, and establishing a significant presence in space all represent crucial steps toward Type 1 status. Each advancement builds upon previous achievements, creating a cascade of progress. Education and scientific literacy play vital roles in this journey. As we progress, we need a population that understands and can contribute to these advancements. The democratization of knowledge through the internet represents a crucial step toward this goal. The rate of our advancement appears to be accelerating. Technological progress that once took centuries now happens in decades or years. This acceleration suggests we might reach Type 1 status sooner than some predictions indicate, perhaps within a few centuries rather than millennia. Our journey on the Kardashev Scale represents more than just technological advancement. It's the story of humanity's growth and maturation as a species. Each step forward requires us to think bigger, act more responsibly, and consider longer time scales. What makes this journey particularly exciting is that we're all part of it. Every scientific breakthrough, every technological innovation, every step towards sustainable energy contributes to our progression. We're not just observers of this cosmic journey. We're active participants in humanity's advancement. The Kardashev Scale, while groundbreaking and influential, isn't without its critics and limitations. Like any attempt to measure something as complex as civilization's advancement, it presents a simplified view of a much more nuanced reality. Let's explore these limitations and consider alternative perspectives on technological evolution. Perhaps the most significant criticism is the scale's singular focus on energy consumption. While energy utilization certainly correlates with technological advancement, it may not tell the whole story. A civilization might develop incredibly sophisticated technology that actually requires less energy, not more. Imagine a society that masters quantum computing at room temperature or develops incredibly efficient nanotechnology. Their advancement wouldn't necessarily be reflected in their energy consumption. Consider the possibility of a civilization that develops deep understanding of consciousness and psychic abilities. They might achieve interstellar communication through means we can't yet comprehend, requiring minimal energy expenditure. The Kardashev Scale wouldn't adequately capture such advancement, despite its potentially revolutionary nature. The scale also doesn't account for social development, cultural sophistication, or ethical advancement. A civilization might consume enormous amounts of energy, while remaining socially primitive or ethically questionable. Conversely, a civilization might achieve remarkable social harmony and philosophical insight while maintaining moderate energy usage. Should we consider the latter less advanced simply because they use less energy? Alternative paths of technological evolution challenge the scale's linear progression. Some civilizations might prioritize miniaturization over expansion, developing inward rather than outward. They might create vast virtual worlds or explore microscopic frontiers rather than reaching for the stars. Their advancement would be no less remarkable, yet might not register significantly on the Kardashev scale. The assumption that technological progress necessarily means expanding energy consumption might reflect our own industrial age biases. Future developments might focus on efficiency, sustainability, or entirely different paradigms of existence. A civilization might discover ways to tap into dark energy or manipulate quantum fields with minimal conventional energy usage. Consider biological advancement as an alternative metric. A civilization might focus on optimizing their own biology, achieving remarkable capabilities through genetic engineering or biological technological integration. They might develop biological computing systems far more sophisticated than our electronic ones, yet potentially using less energy. The scale's focus on macroengineering projects might miss equally important microscale achievements. Mastery over atomic and subatomic processes, manipulation of quantum states, or control over fundamental forces might represent huge technological leaps without necessarily requiring vast energy consumption. Information processing capability presents another potential metric for advancement. A civilization might develop incredibly sophisticated ways to process, store, and manipulate information without corresponding increases in energy usage. Quantum computing, for instance, might enable computational feats far beyond our current capabilities while potentially using less energy than classical computers. The scale also doesn't account for possible paradigm shifts in our understanding of physics. Future discoveries might reveal entirely new ways to interact with the universe that don't rely on conventional energy consumption. What if a civilization discovers how to manipulate space-time directly, or finds ways to access parallel universes? Cultural and artistic achievement represent another dimension missing from the scale. A civilization might develop forms of expression and creativity far beyond our comprehension, creating works of art that transcend physical limitations. Should this not count as advancement? The assumption that bigger is better, that controlling more energy necessarily equals advancement, might reflect limited human perspective. A truly advanced civilization might find ways to achieve their goals while minimizing their impact on the cosmic environment, practicing a kind of universal sustainability. Some critics argue that the scale's linear progression doesn't account for possible recursive or cyclical patterns of development. A civilization might choose to expand and contract cyclically, or might discover that certain forms of advancement require periodically scaling back energy usage. The role of artificial intelligence presents another challenge to the scale. As AI develops, the very nature of civilization might change. Would an AI-driven civilization necessarily follow the same energy consumption patterns as biological civilizations? They might optimize for entirely different metrics of advancement. The scale also doesn't address the possibility of non-physical advancement. If a civilization transfers its consciousness to virtual realms or evolves beyond physical form, how do we measure their energy consumption or technological level? Their advancement might take forms we can't currently comprehend. Time-scale compression represents another limitation. A civilization might develop ways to manipulate time itself, achieving effective immortality or massive computational power by optimizing time rather than energy usage. The Kardashev Scale doesn't account for such possibilities. Alternative evolutionary paths might prioritize cooperation with natural systems rather than their domination. A civilization might advance by learning to work within existing cosmic systems rather than trying to control them, developing sophisticated but low-impact technologies. The scale's assumption that civilizations will naturally expand outward might not hold true. Some might choose to expand inward, exploring consciousness, virtual realms, or microscopic frontiers. Their advancement would be no less remarkable, but might not register on the conventional scale. These limitations don't invalidate the Kardashev Scale's usefulness as a theoretical framework. Rather, they highlight the need for more nuanced and multidimensional ways of thinking about civilizational advancement. Perhaps we need multiple scales measuring different aspects of development: technological, social, cultural, and ethical. Understanding these limitations helps us think more broadly about our own civilization's potential development paths. We needn't feel constrained by traditional notions of progress. Our advancement might take forms that Kardashev never imagined, following paths that emphasize wisdom and harmony as much as raw power. Imagine awakening in a habitat ring orbiting a partially enclosed star, a Dyson swarm capturing most of our sun's energy output. Your morning is determined by the habitat's rotation, creating artificial gravity. The view outside your window includes massive solar collectors, each the size of a continent, gracefully orbiting in precisely choreographed patterns. Transportation in this civilization would be revolutionized. Vacuum tubes might connect various habitats, allowing near-light-speed travel between settlements. Space elevators would make planetary access routine, while antimatter-powered ships could reach the outer solar system in days rather than years. Energy would be virtually unlimited. Personal devices might tap directly into the solar collection grid, providing constant power without need for charging. Manufacturing would occur at atomic scales, with molecular assemblers creating anything needed from raw materials, eliminating traditional concepts of scarcity. The integration of biological and artificial intelligence would be profound. Neural interfaces might allow direct mental connection to the civilization's information network. Augmented reality would be seamless, overlaying physical space with layers of data and virtual experiences. The distinction between real and virtual might become meaningless. Now let's stretch our imagination further, to a civilization spanning an entire galaxy. Individual humans might exist as hybrid beings, part biological, part technological, potentially even pure energy or information. Consciousness could be transferred between different types of bodies or substrates as easily as we change clothes. Distance and time would have different meanings. Using wormhole networks or similar technology, traveling between star systems might be as casual as taking a subway. Some beings might exist simultaneously in multiple locations through quantum entanglement or consciousness distribution. The manipulation of matter and energy would occur at fundamental levels. Stars could be engineered or even created to order. Planets might be terraformed in years rather than millennia. Black holes might be used as both energy sources and computing substrates. AI would be integral to both these scenarios, evolving far beyond what we can currently imagine. In a Type 2 civilization, AI might manage the vast solar collection infrastructure, maintaining the delicate balance of energy distribution and habitat maintenance. By Type 3, AI might evolve into something we would barely recognize as intelligence. It might become a distributed consciousness spanning the galaxy, managing the unimaginably complex tasks of coordinating a civilization across thousands of light years. The relationship between biological and artificial intelligence might evolve into a symbiosis we can barely comprehend. Rather than remaining separate entities, humans and AI might merge into a new form of consciousness, combining the creativity and emotional intelligence of biological beings with the processing power and precision of artificial systems. The Kardashev Scale serves as both a mirror and a window, a mirror reflecting how far we've come as a civilization, and a window showing the breathtaking possibilities that lie ahead. As we stand here, a civilization not yet even at Type 1, we can feel humbled by the magnitude of what's possible and inspired by the journey ahead. While the Kardashev Scale focuses on energy consumption, our advancement encompasses much more. We're not just developing technologically, we're evolving culturally, socially, and philosophically. Our journey to the stars must include advancing our wisdom, ethics, and understanding of our place in the cosmos. We can see the path ahead. Sustainable energy, space exploration, artificial intelligence, biotechnology. These aren't just scientific pursuits. They're stepping stones toward becoming an advanced civilization. Each breakthrough in these fields brings us closer to Type 1 status and beyond. The gap between where we are and where we could be might seem vast, but remember, every Type 3 civilization must start somewhere. Our dreams of harnessing the power of stars and spanning galaxies aren't just fantasy. They're possible futures waiting to be realized through human ingenuity and determination. If this exploration of the Kardashev Scale and our cosmic potential has expanded your horizons, remember to support Exploring the Universe by liking this video and subscribing to the channel. Each subscriber becomes part of our community of cosmic explorers, joining us as we continue to investigate the wonders of the universe. Together, we're not just watching history unfold, we're helping to write it. Every view, every share, every conversation sparked by these ideas contributes to humanity's collective journey toward the stars. By staying curious, engaged, and supportive of scientific advancement, you're helping to push our civilization forward. The question isn't whether humanity will advance along the Kardashev Scale, but how and when. And most importantly, what role will you play in this greatest of all human adventures? Join us on this journey. Together, we'll explore the universe, push the boundaries of what's possible, and work toward a future among the stars. The cosmos is calling, and through channels like Exploring the Universe, we're answering that call, one video, one discovery, one step at a time. Let's keep dreaming big, thinking critically, and reaching for the stars. The journey to becoming an advanced civilization isn't just about technology. It's about people like you who dare to imagine what's possible and work to make those possibilities real.